while having all the data which is magnitude table and phase angle table, then we can plot the Bode plot. So this is the semi-log graph sheet. Then I can choose the proper frequencies over top of it. Then the left side I can take the range of MdB values. Then the right side I can take the corresponding phase angle values in degrees. Now, so we know that in magnitude plot there are 4 frequencies that are to be plotted. At omega is 0.1, then I need to take 20 dB. So plus 20 dB I can take here. Then again it goes to 0 when omega is 1. Then again it goes to minus 80 when omega is 100, and it goes to minus 98 when omega is 200. So all the slopes are decreasing, and we can write here what will be the corresponding slope. So initially I have 20 dB, then I have minus 20 dB for decade, minus 40 dB for decade, minus 60 dB for decade. Now similarly the set of values available for the phase angles. So from the phase angle table I can look at all the points for the phase angle table and draw the smooth curve, that will be the phase plot. So having this magnitude plot and phase plot, then we can find what are the critical values we have. So first of all we will try to find what is the gain crossover frequency. So the gain crossover frequency is the frequency at which the magnitude plot at k is 1. At k is 1 we plotted this at k is 1. So it is crossing the 0 dB line. So it is very clear 1 itself is my one of the crossover frequency, corner frequency. Therefore omega 1 it is 0 dB. So omega GC is nothing but now 1 radian per second. Now at this omega GC I can look at what will be the phi GC. The phi GC is going to be minus 140 degrees. Then phase margin is 180 minus 140 degrees, that is 60 degrees. Phase margin is 60 degrees in this particular case. Next look at what is the phase crossover frequency. Now already phase plot is available, we have a reference with minus 180 degrees, it is crossing minus 180 degrees. So when it is crossing minus 180 degrees, then look at what will be the omega value. That omega value, omega PC is 3 radian per second. So at this 3 radian per second, then I just draw the vertical line onto the magnitude plot. So when you draw vertical line onto the magnitude plot, the point intersecting will get it as minus 18 dB. So MdB value at that MdB PC will be minus. What will the gain margin in dB? Minus of MdB PC. Then minus of that will be 18 dB. So when you take k is equal to 1, the phase margin is 60 degrees and the gain margin is 18 dB. So my system is a stable system. The second case, for the same system, if we want to have gain margin as 5 radian per second, what should be the value of k? How can you tune my value? Initially we have taken it is 1. Now, so magnitude plot is available. When k is 1, what is omega GC is 1 radian per second. But now I want to make it 5. So at 5 radian per second, what will be the MdB value? So if you look at that is going to be minus 24 dB. But for our case, what we want is, I want at omega GC is 5 radian per second, the magnitude value should be 0 dB, which means I need to shift this magnitude plot upward direction by 24 dB. So since we are moving it upward direction, then I should take the plus value. So what will be that? 20 log k is equal to plus 24 dB, because we are shifting that upward direction. And we can find out what is the corresponding k value. So corresponding k value is 15.84, means as we know, when k is 1 we have omega GC is 1. Now if you increase the k value to 15.84, then now it is become 5 radian per second. Since you are shifting upward direction, k is increased. So if at all, if there is a need to shift downward direction, then k will decrease, the k will be less than 1. In this case it is greater than 1 because of the upshift. So this way we can find out the k value for any given omega GC. Sketch the Bode plot for the system whose open loop transfer function is given by GH of S is equal to 15 into S plus 5 divided by S into S square plus 16S plus 100, and determine the stability of the system, right. So in this problem, we have open loop transfer function, but the denominator we have a quadratic term. And we know how to get the corner frequency and also corresponding magnitude and phase angles for the quadratic factor. So using that, we will try to plot the magnitude and phase plots and we find the stability of the system. So first let us look at the transfer function. So the transfer function is having the quadratic factor. So from the quadratic factor, we will find out what is a zeta and omega n. So when you look at, when you take this quadratic factor separate, that is s square plus 16s plus 100. Now when you equate this to a standard characteristic equation, the standard characteristic equation is s square plus 2 zeta omega ns plus omega n square. When you compare, omega n is going to be 10. Then again if you compare the second term, 2 zeta omega n into equal to 16, then by substituting omega n value, you will get zeta is 0.8. Now omega n values available and zeta values available. So once these two are available, now go back to the transfer function. The transfer function is not in the standard form. So the standard form required for the Bode plot is a time constant form. So let us convert this into time constant form. So we know that your gh of s is 15 into s plus 5 upon s into s square plus 16s plus 100. So in the numerator you can take 5 common, denominator you can take 100 common. Let us do that simplification. You are going to get it as 0.75 into 1 plus 0.2s divided by s into 1 plus 0.01 s square plus 0.16 s. Now you can substitute s is equal j omega to get the sinusoidal transfer function. Therefore the sinusoidal transfer function is going to be gh of j omega. In the numerator I have 0.75, 1 plus 0.2 j omega, and upon the denominator I have j omega. So when you do that, when you substitute that omega, j omega, s is equal j omega, so s square term is going to be minus. So then the real part in the quadratic term is 1 minus 0.01 omega square plus j 0.16 omega. So this is the transfer function, sinusoidal transfer function in time constant form. So once this is available, then we will start with the magnitude plot. So in magnitude plot we have steps. Let us take the first step. So in the first step, identify what are the corner frequencies and arrange them in the increasing order. Then if you look at the transfer function, there is a one finite 0. For that you will get one corner frequency. In the denominator I have a quadratic factor. Whenever you have quadratic factor, again you will get one more corner frequency, two corner frequencies. So when you write in increasing order, so your omega c1 is going to be 5 radian per second and omega c2 which is omega n, because whenever you have quadratic factor, the omega n is the corner frequency, omega n 10 we got it. So omega c2 is 10. So 5 and 10, these two are the corner frequencies. Now assume omega L as usual 0.1 radian per second and omega H is greater than 10, let us take it is 20. So for these four corner frequencies I need to find MDB values. So for that let us look at the step 2, the table preparation. In the table we know the columns, the first column is corner frequencies, the corresponding terms and the slope of the particular term and the change in slope. So when you look at the first row, so there is no frequency at all, but here I need to take the first term from the transfer function. The first term is 0.75 by s or 0.75 by j omega. So there is a one pole in the denominator. Therefore, the slope will be minus 20, which is the initial slope of the magnitude plot. So S naught, therefore same S naught is change in slope also. So that will be minus 20 dB for decade. So coming to the next corner frequency omega c1, which is 5. So this corner frequency is of the finite 0. So since it is 0 and there is only one 0, therefore the slope of the particular term is plus 20. Already minus 20 is there, plus 20, then it is going to be 0 dB for decade. Then the next corner frequency is your 10. So this is of the quadratic factor, which is in the denominator. So the quadratic factor, the denominator, it is minus. So quadratic means it is a second order, therefore I need to take the minus 40. So minus, because the denominator, quadratic factor 40 minus 40. So already I have 0, 0 minus 40, it is going to be minus 40. So I have initial slope is 20, then after that 0 dB for decade, then after that minus 40 dB for decade, and from this table, and they are useful to find the MDB values for all the frequencies which are available. So in step 3, for two frequencies, that is when omega L is 0.1 and omega C1 is 5, then we are going to find what are the MDB values. For that, let us take the first term. The first term is 0.75 by j omega. The magnitude is 0.75 by omega. Then what is MDB? 20 log 0.75 minus 20 log omega. So when you substitute omega values, so when you substitute initially omega value is omega L, that omega L is 0.1, then it is going to be 17.5 dB. This is the MDB value at omega L. Similarly, for the same expression we can take it and substitute omega C1, that is 5 radian per second. When you substitute, it is going to be minus 16.5. So 0.1 corresponding will be 17.5, then it is increased to 5, then we have a drop in the magnitude dB, that is minus 16.5.